Pleased this time to have a visitor from our neighboring institution, Southeast Missouri State University. Pleased to have Sheng with us this morning. You can see his title. We look forward to hearing your talk.
Thank you. It's really my honor to have a chance to give presentation here. And today I'm going to give a talk about a delayed epidemic model. And we will introduce the technique of Lyapunov functional to analyze the global asymptoticity of the solutions for this epidemic model. And if you have any question or if there's anything clear, please feel free to stop me, to interrupt me. I'm very happy to communicate during the talk. Just try not to save the question to the last minute. So feel free to interrupt me. So this is the outline. We will first start with a very simple but also very fundamental epidemic model which has no delay. And using this model, we will illustrate the idea of the Lyapunov function technique, and we will analyze the global stability of the equilibrium for this simple model. Then we will mainly focus on the general systems. When we introduce a delay, we will introduce delays to this model, and we will state an open problem. So far, as I know, still is open, and we will present some partial answers to this open problem. So some recent progress, and we will study some special cases for this general delayed model. And then we will make a conclusion. So this is our first page. We'll start from the very simple but fundamental epidemic model. So this is the disease model. We will analyze the spread of disease in population of people or of species. We assume that the population is separated into two classes, very simple two classes. One class is the susceptible class, which has not been infected yet, but may be or may not be infected. And there's another class, the second class is called infected class, which they are infective and they may transmit the disease from themselves to the susceptible classes. So we have two classes, susceptible classes and infected classes, denoted by S and I. S is the first letter of susceptible, and I is the first letter of infected. And T denotes for the time, as usual. So all of this population, we assume that they are positive. And we studied the following two equations, differential equations. S prime T, I prime T denotes for the derivative of the function with respect to the time T. So S prime T is the change of the susceptible population. So we will have input B. B denotes for the birth rate. And then we will have output leaving this population by disease transmission. So it becomes infected. So this is nonlinear transmission, nonlinear disease transmission. It depends on the population of S, depends on the population of I, and also we use a constant beta denotes for the transmission rate. So it's proportional to S, proportional to I. So it's bilinear function. And then we also have natural death, mu S. Mu S is the natural death rate. So it's mu S times S. And then we also have input coming from I. It's Q gamma. We'll talk about that later. And then look at the equation for I. We have input. It comes from the susceptible population, which have been infected, become infected. So we have SIT coming from S. And then we have the death rate, mu I times I. In general, we may not have the same death rate for susceptible person and the infected person. So we have mu I and mu S denotes for the death rate for infected class and the susceptible classes respectively. And also we have gamma. Gamma denotes for the recovery rate. So we assume some infected person will become immune to this disease after recover. So it's just we have this is the recovery rate, gamma times I. So it means that there's some population we are leaving this disease transmission cycle. We leave this transmission cycle. But as we have observed in some disease, that sometimes the person after getting immune from the disease, the immune may lose. The immunity may lose at some probability. So we use the probability Q, constant Q between 0 and 1 denotes for the probability of immunity loss. And if the immune class, the infected person, the immunity of the infected person is lost, so it becomes susceptible again. So it becomes susceptible to the disease again. So it comes back. That's why we will have additional term Q gamma I in the equation of S. We have Q gamma I in the equation of S. So you can imagine this kind of cycle. S becomes I by the disease transmission, but I will go back to S because the immunity loss. There's a Q denotes for immunity loss between 0 and 1. So this is, yes?
I should not expect S prime and I prime to sum to 0, should I? S prime plus I prime, I think, should not be 0, right?
Should not be there, yes.
Okay.
In general, they are not 0. No.
And so the immunity loss, you assume, is immediately after they recover. Some of them are
That's good
susceptible
question.
again. It's not like after 5 years they become susceptible again.
That's good question. So we are talking about a general model after the simple OD model. So in that model, we are taking account of the delay of immunity. But currently, since we only want to focus on the very simple model without delay, yes, that's a very good question. Let's suggest that we'll talk about general model later. So kind of we do not assume there's kind of immunity loss delay. So we just immediately become susceptible. Immediately, everything is just immediately. And also from the S to I, we also assume that immediately. As long as the beta SI leaving the S class, you will immediately go to I class. But later on, we'll include delay into that process. So you see that this is just two-dimensional ordinary differential system. So all of these constants, B, beta, mu, S, mu, I, Q, gamma, they are all non-negative, right? And most of them are positive. So Q may be 0. If Q is 0, means that there's no immunity loss. It's just very special case. So first we analyze the equilibrium. We want to understand what will be long-term behavior of the solution if you are given any initial value, positive initial value. What will be the long-term behavior of the solution? And to analyze that, we first will analyze the equilibrium. So we just set the derivative equal to 0. Left-hand side is 0. And we just solve this linear, non-linear system, two-dimensional non-linear system. And we can find there are two solutions. One is called disease-free equilibrium. So if you look at the equation for the second one, we can see that we can factor I out. Now we want to solve for S and I. We are given the constant B, beta, mu, S, mu, I, Q, gamma. We want to solve the variables S and I. So from the second equation, you can see that the simple solution is that I equals 0. And if I equals 0, we plug in back to the first equation, we can get S equals B over mu S. So this is our first simple equilibrium. It's called a disease-free equilibrium. And the second case is that if I is not 0, and again we look at the second equation. If I is not equal to 0, we can factor it out. We can divide by I. We can get so for S equals mu I plus gamma divided by beta. So we solve for S, and then this denotes as S star, and then we plug in back into the first equation. We can get I is given by this fraction. And also we notice that on the second equilibrium we call it epidemic equilibrium. We have S star should always be positive because every parameter is positive. But let's look at I star. I star is a fraction of two differences. And in bottom, the denominator, we can observe that it's always positive. Why? Why is always positive? Because we assume that Q, the probability of immunity loss, is always less than or equal to 1. So Q is less than or equal to 1. And then gamma is less than mu I plus gamma I. So if you compare these two quantities, you can see that the difference in the denominator is always positive. So we conclude that I star is positive if and only the numerator is positive. And the numerator of this fraction is positive is the same as say that B beta is greater than mu S times mu I plus gamma. This inequality will appear lots of time throughout this talk. So I want to emphasize on this inequality. This inequality is a very important criteria in our determination of global stability of equilibrium. So we know that if this condition is satisfied, which means that B is very large or beta is very large. B denotes for the birth rate, beta denotes for the transmission rate. So if the transmission rate is very large, then we may have the endemic equilibrium. I star is positive. If I star is negative, then this equilibrium is not biologically meaningful. So we always have this condition if we want to have endemic equilibrium. B beta is greater than mu s. Mu s is the death rate of susceptible population, and mu I is the death rate of infected population. Gamma is the recovery rate. So we have two equilibrium. One is the disease-free equilibrium when I equals 0. Another one is endemic equilibrium, which exists if and only if this condition is satisfied. And this is the result. So suppose we are given any initial positive value, we always assume that population are positive. And then the disease-free equilibrium as 0, I equals 0, is globally asymptotically stable if and only if B beta is less than or equal to mu s times mu s plus gamma. You see that this condition guarantees that endemic equilibrium does not exist. So there's no other positive equilibrium. There's no other equilibrium because this condition is just violates the existing condition of endemic equilibrium. So if this condition is satisfied, B beta is less than or equal to the quantity on the right hand side, then we have that the disease-free equilibrium is globally stable, which means that all of the solution with positive initial value will always tend to this disease-free equilibrium, which means that the disease will disappear eventually. If this condition is satisfied. On the other hand side, if we reverse the inequality, if B beta is greater than the quantity on the right hand side, which means that we can think of that beta is very large, the transmission rate is very large, the disease is very serious. Then the endemic equilibrium will be globally stable, which means that all of the solution with positive initial values will always tend to the endemic equilibrium. So this is the main result for the simple ODE model. And we have simply state the idea of the proof. The proof is just using the Lyapunov functional technique. We just need to construct simple Lyapunov functions for the disease-free equilibrium to prove the disease-free equilibrium, global stability of that equilibrium. And then we construct another Lyapunov function to prove the global stability of the endemic equilibrium. So you can see that that condition, B beta greater or less than the quantity on the right hand side, is the criteria. So this is the construction of the Lyapunov function for disease-free equilibrium, the first Lyapunov function. And later on, you will see lots of another type of Lyapunov function which is very similar to this one, just based on this form. So you can see this is just, so assume that we have two variables, x1, x2, which correspond to our two-dimensional system. And we just define the right-hand side is just quadratic function. x1 minus s0. S0 is constant, is the b over mu s. B over mu s is just constant, plus s2 squared. Right? So it's the quadratic function of x1 plus x2. And also add x2, add a linear function in x2. It's a quadratic function or linear function. So this is a typical Lyapunov function, quadratic or linear. And the coefficient is just constant. It's just constant. And if we restrict this Lyapunov function around the solution, and we will have this formula. We just replace x1 by xt, x2 by it. And we want to show that the derivative of u around t around the solution is negative or 0. It's always non-positive, which means that the solution eventually will tend to the disease-free equilibrium. So we construct this Lyapunov function, and then we want to prove that the derivative of this solution around the solution with respect to t will be non-positive. And the proof is also simple. So we have the ODE system, and we just take derivative. We just simply take derivative, apply the quotient rule, and then using the ODE system, so we will have the derivative of s, derivative of I. We just plug in, and we just arrange them properly, and eventually we have a negative of squares. Negative of squares. You can see there is a negative, and on this big quotient, the denominator is always positive constant. It's positive constant. And on numerator, we have a square here, and we have another square here. And this is again is a positive or non-negative constant. And so the first quantity is always less than or equal to 0. And the second quantity, we have IT. We know that the population is always positive. We can prove that if the solution, initial value is positive, then the solution is always positive. So IT is always positive. So we only have the quantity in the bracket is B beta minus mu S times mu I plus gamma. And this coincides with the condition that B beta less than or equal to mu S times mu I plus gamma. So this quantity is less than or equal to 0 because we have the assumption, we have the condition that should be negative or 0. So eventually the summation of these two will be less than or equal to 0. So this is the basic idea of the proof. We first reconstruct the simple Lyapunov function, and we prove that the derivative of this solution with respect to t is less than or equal to 0. Then we can apply the Lazare invariance principle to get the global stability of these three equilibria. Any questions so far? So you can see that the proof is not quite difficult. It's just we need to have some luck, or we need to have some experience in constructing the Lyapunov function. So in most of cases, if we have found a simple Lyapunov function, then we are done. Okay. All of the rest part is just verify the derivative is less than or equal to 0, and just simply apply the Lazare invariance principle. Yes, please.
So how you show the IT is also corrected?
Oh, yeah, that's a good question. So basic idea we just prove it by contradiction. Prove it by contradiction. But for IT, it's simple because we can say that the right-hand side, let's look at the equation for epsilon t. The right-hand side is just IT. If we divide by IT on both sides, and we take integral, or we can say that we can express IT as the expansion of integral. We express this as IT as the expansion of some quantity. So expansion function is always positive. That's the basic idea from this one. Because the right-hand side we can factor IT out. So we just basically just simply integrate both sides. Integrate both sides. So we can prove that IT is positive if the initial value is positive. Is that clear? And for ST, we have to prove it by contradiction. The positiveness of ST we just need to prove by condition. Assume that is not positive, then we can prove. Then just using several lines, we just can verify that it can never happen. Any more questions? Please feel free to interrupt me. So this is the first part. And the second part is that if that condition is reversed, okay, so now we have strictly greater than, then we have the endemic event exists. And we want to prove that if it exists, then it should be globally stable. Globally asymptotic stable, which means that all of solution is the positive continuous cancel that out. So we construct it like this. This is another type of Lyapunov function. You can see that it's not quadratic, it's not linear, but we have log inside it. So we denote as V, capital V. Previously it was U. So V is a two-variable function, and we have x1 minus s star is just constant times ln as x1. Okay. So you can imagine what's the graph of x1 minus x star ln x1. It looks like the quadratic function. It looks like quadratic function. And also we have x2 minus I star times ln x2. Okay. So this is another typical type of Lyapunov function. Another typical form of Lyapunov function. So by experience, if we want to look for simple Lyapunov function, we can try linear function, we can try quadratic function, positive function, polynomials. And if that doesn't work, then we can try this form, log type. And here we just basically comment that the denominator is positive, so the coefficient should be positive. So this is simple. And then we restrict this Lyapunov function along the solution. And then we want to prove, as usual, we want to prove that this is negative. So again, we have to make use of OD system, and we just take derivative, apply the chain rule, and we just carefully arrange all of terms so that we will have negative of something squared. Negative of something squared, and we prove that this is less than or equal to 0. So you can say that we have negative of something squared and minus another squared. So it's always less than or equal to 0. Then we just apply the Lyapunov Lazare invariance principle, and we can get the globally asymptotically stable with stability of the endemic equilibrium. And here we have to make use of the inequality. We have made use of the fact that I star is positive. I star positive means that beta, that condition is satisfied. So we have notice that we have coefficient beta I star of the second square. We have to make sure I star is positive. So that in that case, in that step, we have used the condition that B beta is greater than mu s times mu s plus m. So that condition always appears somewhere. So this, yes.
So my question is how you find that Lyapunov function?
Yeah, that's a good question. So I can tell you that just by experience. So just look at the literature. Somebody else used this type of Lyapunov function to prove other type of equation, and we just follow that, and we just check that whether this works. And we have to manipulate a little bit, and sometimes we have to be carefully choose the coefficient. Even though this constant coefficient is not easy to figure it out, we have to try. We have to make lots of try.
Solves the PDE inclusion LV of the generator is more like 0. That's on mathematical. Just the mathematical paper can't do it because they are not able to handle the differential inclusion. PDE inclusion.
So throughout this talk, we'll just meet this type of Lyapunov function. So projective function, linear function, and this log type function. Now we'll go to the main part of this talk. This is the main model we're going to introduce today. So the only difference is that now we introduce the delay, which makes the model a little more realistic. So we can just make the model better and better, but we can never find the best model. We just want to take something into consideration, and we want to include that in our model, and we want to analyze this model to see what phenomena we will have. For instance, here, we first assume that there's a delay during the disease transmission, which means that if some individuals got infected, they will have some kind of latency period. So during that period, this individual is not infected. But after that period, then the person becomes infected. So that period is called latent period. And we assume that there is kind of this delay here. So that's why we have the equation for I prime is not just immediately beta times IT, but we assume that there's kind of delay tau. There's kind of delay tau here, and tau denotes for the latent period. And this is, for general case, we just assume that this is distributed delay. So P1 tau is just the distribution function, distributed population probability function. It's just a probability function. And in a very special case, you just say P1 tau is the data function, so this is just a single delay. And we will look at some special cases for P1 tau. So this is just a slightly general form of the delayed model. So if we want to introduce delay, so this is the general case of delay. Yes?
Is there an advantage in modeling the delay this way instead of having a separate state for recovered and then a gradual exit out of that into susceptible again?
That will be included in this model. We are
okay.
So that's why I call this is the general model. So that case will be included. We'll see that later. And also we will have delay for the loss of immunity. So that will count for the P2 tau. P2 tau counts the probability density function for the delay of immunity loss. And for this model, I can say that there's no clear answer for the global stability of equilibrium. But we will study some special cases which will cover the case what you mentioned. So first we just assume that there's only one delay. We assume that there's only one delay in the disease transmission and no delay in the immunity loss. So there's no item factor as no delay in that. So we can calculate the disease frequency. We just simply set the left-hand side to 0. We just assume the SI are constant. They are constant, and then we can find, again, we will find two equilibria. y is the disease-free equilibrium. And another one, for simplicity, we just denote this constant. This constant is slightly less than beta, slightly less than beta. Okay. And then we have the second equilibrium, endemic equilibrium. It has very similar form. The only difference is that now the original beta becomes now beta 1. Now becomes beta 1. And then we can prove that this again is just kind of criterion. So if we have less than or equal to, which means that the disease transmission is not so serious, then the disease-free equilibrium is globally stable. And if we reverse the inequality, which means that the disease transmission is a little bit large, beta 1 is large, the disease is very serious, so that the endemic equilibrium is globally asymptotically stable. And the proof is similar. We need to construct the Lyapunov function. Now we call it functional. Now we call it function because we have delay. Because the state space is different. For the ODE system, the state space is just two-dimensional plane. It's just two-dimensional. It's just a point in the two-dimensional plane. But now for the delay differential equations, the state space now becomes functional space. Now becomes function. So this is just the main difference between the delay differential system and the ordinary differential system. So everything we just translate the metric theory into the functional theory. So everything becomes function space instead of just finite dimensional space. And we just need to be a little bit careful about that. So here we just introduce the function space. It's the Banach space, which consists all of continuous functions on negative real line. And we also assume that since this line is not compact, so we cannot apply the usual maximum norm to make it a Banach space. We have that. Modify a little bit, we just introduce this weighted norm to make sure that this is complete space. So this is just a little bit technique in functional analysis. So we introduce this space. We just keep in mind the space now is continuous function, not just a point. So the state space is just continuous functional space. And we define the Lyapunov functional because the domain now is function space. So it's called functional. It's defined as this way. And you can see that it's very similar, even though it's a little bit more complicated. It's very similar. We will have a quadratic function, x1 0 minus s0. S0 is constant plus x2 0. So it's quadratic. And then we have the linear x2 0. And the third term is just the integral, which we have to take care of. We have used this one to cancel out the delay terms because we have delay in the equation. So we need this term to cancel out the delay. So this is just a technical term. But the main idea is just a similar square function or linear function. So if you like, I can send the PDF file to you. You can come back to me. So if you do not have time to copy down this formula, you can just come to me after the lecture.
One requires theta in value.
Which one? Theta less than or equal to 0. Because the function space is on negative real line. From negative infinity to 0. It's not dependent on the whole real line. So we can think of this way. If we have ordinary differential system, we just need, if we are given the initial state at t equal to 0, if we are given the initial point at t equal to 0, then we can move on using the ODE system, ordinary differential system. We just need the history at t equal to 0. But now if we have a delayed differential equation, we need the whole history from negative infinity to 0 in general, all of the history. So that's why the state space is a function of negative infinity to 0. You can imagine that for the ordinary differential system, we only need to use the history at t equal to 0. So that's just one point. But now for the delay, it's from negative infinity to 0. So it's just a function on the real line, on the negative real line, on the negative real line. So this is our Lyapunov function, which is very similar similar to the one for the ordinary differential equation. And then this is another Lyapunov function for the endemic equilibrium, which also again very similar, even though a little bit more complicated, but very similar to the one. Actually, basic idea comes from the one for the ODE system. So we have the log type. We have 3 parts. Vs comes from the is a function dependent on x1. So it's just we have x1 0 times s minus s star is a constant times log, so it's just log type. And with I is also log type. And that's v minus, we use minus just denote for delay term. So this just take care of the delay. We want to introduce this term to cancel out the delay. So basic idea is that for the endemic, we just use the log type. And then, so this is just one partial answer. If we have only one delay, and then other delay, the delay for immunity loss is not or is not. But now we take care of the immunity loss delay. So this is the general delay function, the general delay system. And we look at the case, again we look at the special case, because for the general case we have nothing about the general case, there's no clear answer about general case. So we only look at the very special case when P1 tau is the delta function. If P1 tau in the integral, the integral is delta function, which means that the integral reduced to just at one point. So if P1 tau is the delta function at T1, so that integral becomes just the only one delay term, T minus tau 1. It just evaluated as tau 1. It's just the function evaluated as tau 1. So we have just single delay term. And also, we'll go look at P2. Let's assume that P2 is an exponential decay function. P2 is the exponential function. And let's look at the equation for s prime t. So we have the integral, and we replace P2 by this exponential function. And we introduce a new quantity denoted by R. And this R has biological meaning later. I will explain that in a bit. So let's first formally we look at R is just the integral. R is just the integral. So the equation for S has only R, has only RT. No delay there, it's just RT. And then for the R, we can take derivative. We can take derivative of R, and we see that for the derivative of R is also very simple. It's just Q gamma I minus some constant times R. So we can see that if the very special case, if the P probability density function is exponential decay function, then we can reduce the delayed differential system into a higher dimensional ordinary differential system. A little bit higher dimensional. We now have one more dimension. We have R term, but now everything is just ordinary differential. There's no delay for this quantity. So we can get rid of the delay if the probability density function is just very special exponential case. And this is a very famous trick. It's called linear chain trick. And then eventually we have just this system. Now we have three variables, S, I, and R. R denotes for the recovery class. R has the biological meaning, it's called the recovery class. And now we only have the delay from S to I. From S to I, we only have a delay for the immunity. And the delay of loss of immunity is just taking into account of the, if we introduce the new quantity R, which has biological meaning, it's called the recovery class. So this is called SIRS mode. So you can see first from S to I, and then from I to R, then R will go back to S. The recovery will become successful again. So for this case, for this system, again we have two equilibria. And one is discrete, one is endemic. So I will skip the detail. And then we also need to introduce the state space. But now since we only have a constant delay, so the state space is simpler. It's just the continuous function space on the compact interval. So because this is compact, so we can just use the super norm to make it finite space. And then we introduce the Lyapunov functionals. Why is Lyapunov functional for diffuse equilibrium? This is simple. But there's a slight change. Now for this one, we tried to use the projector again, but it didn't work. That's why we used the log. You can see that now for the x1, we have log here. previously it was square for the disease free, but now we have used the log type. We have used the log type Lyapunov function. The second one is just linear. X2 is just linear. But for x1, now we have x1 0 times minus s0 times ln. We have log type Lyapunov function. And this one works, but it's not perfect. Let me explain why it's not quite perfect. Because if we take the derivative of u, this Lyapunov function, and we can see that we have that it's bounded by the right-hand side, it's given by here. And inside the big bracket, there's quantity, which we cannot guarantee that it's always negative. So that's why we need to introduce the technical condition. So this is why it's not perfect. So we need to introduce this technical condition. We remember that the general condition for in general we want that the perfect condition is that we do not have the term colored in red. If there were no term colored in red, so this is perfect, because this is the natural condition. But for this problem, unfortunately, the only thing we can get is just we need this technical condition to make sure that this is free equilibrium is globally stable. Yes?
So are you always assuming it's globally stable, then you try to construct the Lyapunov function?
It's not that we assume that we can do lots of simulation to say that it is globally stable. But we want to prove it mathematically. We want to prove it mathematically. So we believe that it is globally stable.
But if you can't find the Lyapunov function, doesn't mean...
It doesn't mean that it's not true. It just means that we failed to prove it, but it doesn't mean that it's not true. Or it doesn't mean that it is true or not. Because we believe that it's true because we have done lots of simulations. As long as we have the system, we can plug in any initial values to check whether the solution goes. And we verify that if that condition is satisfied without the red term, if that condition is satisfied, always go to the disease free. And if that condition is violated, always go to the positive. There's no other choices. So simulation suggests that we have this theorem. We should have this theorem. But unfortunately, the technical part, the mathematical part, we cannot build in this step. We cannot find the best Lyapunov function to prove it is true. So we just try to approach that objective. So that's why we can check this Lyapunov function, and we can prove that it is true. It is correct under some additional technical condition, which should not be there, but we need that to prove it. In our proof, we need that. But I hope someone else in the future can get rid of this condition. That would be great. So this gives us the question. So we know that for this system, from simulation, we always see that this should be true. But we need this technical condition to prove that it's true. And on the other side, for the endemic area, we have no, even though we cannot impose any technical condition to prove that, so we have no idea how to prove that. We have tried the log type Lyapunov function and it doesn't work. So this only gives us just a few things. Yes? So this is the second special case. The solution is not so satisfactory. It's not so good, but this is just partial answer. So let's look at one last special case. Again, we start from the general delay system. And then we notice that if we assume that the P2 is the expansion function, it's the same as we just introduce one more term, introduce one more class, say R class, so that it becomes ODE. And similarly, if we said P1 is also expansion function, expansion decay function, because its probability function is always decaying. The expansion function, then we can reduce this to another ODE system. To the ODE system by introducing one more term. So this is basic idea. So basically, we just take some special case for P1 and P2. Special case means that we take the exponential case. Then this delay differential system eventually becomes very simple. Looks very simple, ODE system with higher dimension. So this is basic idea. So we set P2 we just this expansion function. It's a probability function because the total integral should be 1. And also P1 is also expansion function with another parameter r. And for this P2, so we can create that direct term by this integral, and then we just assume, just define this integral to be RT. Define this integral to be RT. So the equation for S, we only have R. And then if we take derivative of this integral, we can see that derivative of R is just depends, it's just a linear in I and R. It's just some constant times I minus some constant times RT. So it looks very simple. And also for the P1, if P1 is assumed to take the very special case, exponential case, then we have this integral and defined as ET. ET also has biological meaning, it's called exposed graph. And then we take derivative of ET, it's also a simple linear function in I and E. It's constant times IT minus constant times ET. So eventually, we can see that we have 4-dimensional ordinary differential system. So again, it becomes ordinary differential system. This looks much simpler. Looks much simpler. And this is the famous SEIRS model. SEIRS model. So we have S goes to E, S goes to E, and E goes to I goes to our alpha vectors. Yes.
I have a question. Is when you take a derivative, is equivalent, or you just up to some shift?
You mean the previous one?
Yeah, when you
take a derivative of E,
yeah.
it's equal. It's just
If I add a constant on the ET, this equation still holds. I mean, you take a derivative, you need to consider that you shift the solution. I know they are the same function, but I could add a constant on ET. Then you take a derivative, the constant term is gone.
But the right hand side should also have one more constant.
No, take the derivative, it's gone.
The left hand side is gone. Yeah. But you mean the derivative of ET plus the constant?
Yeah, I mean, you just think about that. Maybe it's not like equivalent. It's just for one direction. You can come in this way, but you cannot go back. Possible. I don't know.
The behavior is still the same. Okay? If the function E, you get the constant term there, you take the derivative, the constant term is gone, but the behavior, how the function behaves, is the same.
You just shift
So
it
the
up.
common number doesn't make any difference.
So you can imagine that we choose that the constant is 0. We choose that constant to make the equation simpler. Otherwise, the equation will be slightly different. If you say we have a E tier equals E plus the constant, and then what's the equation for E tier? Then should be similar to this one, but now replace E by E tier. Actually, it's replace E by E tier minus that constant. So just make it slightly different, but doesn't make a difference. So we just simply choose this constant to be very special, 0, so that the equation takes the simplest form. So yeah, they are equivalent. But this may take the simplest form. Seems easy to analyze. So finally, we have this. This is a very famous SEIRS model. SEIRS model is just the ordinary differential system with 4 dimensions. And for this one, we have 2 equilibrium as usual. We have these 3 equilibrium. So only S equals the positive constant, and all of other terms EIR are 0. And we also have another one, endemic equilibrium, S star, E star, S star, R star. And also the endemic equilibrium is positive if and only this inequality is satisfied. E beta F is greater than the quantity on the right hand side. So we can conjecture that if the endemic equilibrium exists, then namely if this condition is satisfied, then the endemic equilibrium should be globally asymptotic stable. And this should be true because we have verified this by lots of simulation. We believe that it's true. And on the other hand side, if the inequality is reversed, then the disease-free equilibrium should be globally stable. Unfortunately, there are lots of people who are trying to work on this system for a long time, for 10 years, 20 years. Still, there's no significant progress, which means that there's no one had proved that in a very clear way. Even though we believe that is true, we still couldn't prove it. We need some, in most of previous literature, they just add some technical condition and prove that it's true. But no one can prove it that very simple result. And we also cannot do that. We just need some technical condition. So this is a technical condition to make sure that the disease-free equilibrium is globally stable. And the Lyapunov function, you can see that we just use the log type. We use the linear type and log type. This is our famous Lyapunov function. We just use this Lyapunov function, but unfortunately, we need this technical condition to prove the disease-free equilibrium. And for the endemic equilibrium, we have no idea. So just use this is just a long-term open problem. Even though for this OD system, it's still a long-term open problem. So if someone is lucky, find some suitable Lyapunov function to prove this, that would be great technique on this problem. So you can see that the system looks very simple. It's just only 4-dimensional space.
So is that 10 has any meaning? That red 10, it's a technique.
Red 10?
Yeah, is that
has no significant meaning. It just some depends on the parameters. But it has some meaning. If sigma equals 0, if this sigma equals 0, so this term vanishes. So we can understand in this way. If sigma is very, very small, so this should be true. But what is the meaning of sigma? Sigma, we can say that sigma appears in the equation for R. So there's negative sigma for R. And it goes back to S. It goes back to S. So we have sigma R on the equation for S. So you can see that sigma characterizes the immunity loss. So R denotes for the recovered class with immunity. And if the immunity is lost, then they go back to susceptible. So sigma characterizes the immunity loss. So you can understand this condition that if the immunity loss is very, very small, so most of people will contain their immunity. The immunity will sustain for a long time. It means that the sigma is very, very small. So disease-free equilibrium is globally stable. So this means that if the people are immune to this disease, so the disease will not persist. So we can understand in that way. But still, this is not the best answer. The best answer is that we do not need that reaction. And this should be true. This was verified by the immunity conditions by the study.
But without that term, it is independent of sigma. Right?
Yeah,
you want
it
to
should.
independent of sigma.
Yeah, we should prove that. We want to prove that this is independent of sigma. Unfortunately, we need that. And a lot of literature considering this type of disease model with immunity loss. There are a lot of literature. They always assume that immunity loss is very, very small. Unfortunately. And also on the other side, if we want to study the endemic equilibrium, we want to show that this is globally stable. If this inequality is reversed, but we cannot prove that, we just use this as an open problem. And so this is the last slide, conclusion. So we first start with the a simple ODE system, and we just introduce these two delays. One is the delay during the disease transmission, another is the delay accounting for the immunity loss. And what is our result is that if P2 is a delta function at 0, what's the meaning of delta function at 0? Which means that for that integral, there's no delay in that integral. So if there's no delay for the immunity loss, then global dynamics is clear. And if P2 is exponential function, we can have the global stability of this field under some technical conditions. But the stability of the epidemic influence left as conjecture. And if P2 is general case, we have an idea. That's all. Thank you very much for your attention.
Other questions?
That's the question. You said you verified with numerical methods. Which numerical methods have you used?
We just plug in this equation into MATLAB.
Verifying means mathematical proofs that
not
the
this.
method has the same equilibrium behavior and the corresponding analytic behavior. Which you can do for some models.
Actually, be careful about data that are verified. We just check. Check using lots of
indications.
In some cases, I should never use to verify. We just convince ourselves that this should be, but it's not.
Because the standard numerical method doesn't apply for that. You can prove that they are.
Because we cannot choose all these possible initial values. There's no way we can choose that. So it's not a proof. It's not a computer. It's proof using computer. It's not.
Just you can do it in another way. How do you construct a counterexample which is not stable? You can
we believe that there's no counterexample. If the system is stated that way, we believe that the global dynamics should be that way. So I think it's better try to prove it.
Any others? Thank you.
Thank you.